Welcome to the Explainer. So today we're going to dig into the hidden science that turns a simple rock into, well, pretty much everything around you. Every skyscraper, every car, every single phone in your hand. It all starts with this incredible process of industrial alchemy, a mix of brute force and some seriously clever chemistry.
Okay, let's just dive right in. The basic problem is this: valuable metals almost never exist in their pure form out in the wild. Nope, they're chemically locked inside compounds we call ores, all mixed up with tons of worthless rock. So the whole game, the entire goal of metallurgy, is to figure out how to strategically break those chemical bonds and set the metal free.
All right, to get a little more technical for a second, the metal inside an ore is in what's called a positive oxidation state. Just think of it like this: the metal has lost some of its electrons, and that's what's causing it to bond so tightly with other elements like oxygen or sulfur. Our job, our entire mission, is to force those electrons back onto the metal, reducing its oxidation state to zero and turning it back into its pure elemental form.
So, how do metallurgists actually pull this off? You might think it's just one giant, messy process, right? But it's not. Instead, they use this surprisingly elegant two-step master plan that's been perfected over centuries.
And here's the crucial point: it's all about efficiency. I mean, trying to rip a metal straight out of a sulphide or a carbonate, that's kind of like pushing a giant boulder up a really steep, rocky mountain. It takes a ridiculous amount of energy. But you know, the laws of thermodynamics, they tell us it's way easier to reduce a metal oxide. So the strategy is simple. First, you get that boulder to an easier starting point by turning the ore into an oxide. It just makes that final push to get the pure metal so much easier.
So just think of it like a recipe. First, you prep your main ingredient. You turn whatever ore you've got into a simple metal oxide. And then you cook that oxide with something called a reducing agent to finally get the pure metal. Two distinct stages, one very clear goal.
Okay, so let's break down that first step, making the oxides. There are two main ways to do this prep work, and which one you use, well, that totally depends on the type of ore you're starting with. They're called roasting and calcination.
This slide lays it out perfectly. On the left, you've got roasting. You use this for sulphide ores, and the key here is heating them up in a furnace with a huge blast of air. That oxygen is a really important ingredient. Then on the right, you have calcination. This is for carbonate ore or hydrated ores. And with this one, you actually want to limit the air and just use intense heat to break the whole compound down. So two different starting points, two totally different techniques.
So with roasting, that oxygen from the air is basically used to kick the sulfur out of the compound. The sulfur is perfectly happy to combine with the oxygen, and poof, it turns into sulfur dioxide gas, which just floats away. And what are you left with? The clean zinc oxide we wanted all along.
Now calcination is different. It's not about adding something new to react with. No, it's all about using intense heat to literally break the ore itself apart. For something like calcium carbonate, you heat it up, and that heat forces it to decompose, driving off carbon dioxide as a gas and leaving behind pure calcium oxide. Simple as that.
Okay, so our ingredients are prepped. We've successfully turned our complex ores into much simpler metal oxides. Now we get to the main event, reducing that oxide to finally release the pure crude metal. This is the fun part.
And to pull off this final critical step, metallurgists have a whole toolkit of different methods. The choice of which tool to use, from classic smelting to some more advanced tricks, it all depends on the chemical personality of the metal oxide that we so carefully prepared in step 1.
Smelting. This is the classic method, the one you probably picture when you think of making metal. You know, fire, blast furnaces, the whole deal. It's famous for making iron, and here, carbon, usually in the form of coke, is the hero. The idea is really simple. At super high temperatures, carbon has a much stronger attraction to oxygen than iron does, so it just rips the oxygen right away from the iron oxide, leaving pure, molten iron behind.
And this is where things get really clever. The ore isn't pure, right? It's full of all this sandy, rocky junk. To get rid of it, you add something called a flux, like limestone. The flux basically acts like a chemical cleaning agent. It reacts with all those impurities and forms this glassy liquid called slag. And because the slag is lighter than the molten metal, it just floats right on top, where you can easily skim it off. Genius.
For some metals that are a little less reactive, like copper or lead, you can actually use pure hydrogen gas as your reducing agent. It's a much cleaner method that does the same job as carbon. It pulls the oxygen away from the metal, but in this case, the only thing it makes as a byproduct is water. Pretty neat.
But what about the really tough,
stable oxides like chromium oxide, where carbon just isn't strong enough to do the job. Well, for those, you have to bring in a true heavyweight, a more reactive metal like aluminum. See, aluminum wants that oxygen so badly that it will violently rip it away from the chromium in this spectacular reaction called the aluminothermic process.
And when I say violent, I mean it. This process is incredibly intense. Once you get it started, the reaction generates these extreme temperatures. We're talking up to 2,400 degrees Celsius. That is more than hot enough to produce the pure chromium in a molten state, all ready to be collected.
And finally, we get to the simplest method of all, auto-reduction. Some metals, like mercury, hold onto their bonded elements so weakly that you don't even need a separate reducing agent. You can basically skip the second step entirely. Just roasting the sulphide ore in air is enough for it to practically reduce itself, giving you pure liquid mercury. How easy is that?
So, with all these options on the table, smelting with carbon, using hydrogen, bringing in a more active metal, or just using plain old heat, how does a metallurgist know which tool is the right one for the job?
Well, it all comes back to that chemical personality of the metal you're trying to isolate. How strongly is it holding on to that oxygen? How reactive is it? The answers to those questions dictate the entire strategy from start to finish.
So this table here, it's basically the playbook. For those workhorse metals like iron and zinc, the brute force of carbon smelting is the go-to economical choice. For less reactive metals like copper, a cleaner hydrogen reduction works great. For the really tough, stable oxides like chromium, you gotta bring out the big guns, an active metal like aluminum. And for the easiest ones, like mercury, all you need is a little heat and air. Each method is perfectly tailored to a specific job.
So at the end of the day, what you've got to remember is that this two-step process, convert it to an oxide, then reduce it to a metal, this is the hidden engine of our entire modern world. It is the fundamental chemistry that unlocks the raw materials for nearly everything we build and use every single day.
And that leaves us with a final thought. We have perfected the complex chemistry of getting metals out of the earth. But the next great challenge is mastering the chemistry to put them back into circulation efficiently through recycling, using that same incredible level of ingenuity. Thanks for watching.